All right, well, hello physics students. Welcome to this video lecture, which is just going to take us through the mathematical expressions that we have for these three big energy accounts that we are going to be looking at throughout this unit, and then also take us through the problem-solving process that we can use with conservation of energy. Okay, so first things first, we'll start with gravitational potential. Again, remember, gravitational potential is the energy stored due to an object's position within a gravitational field. Okay, and obviously we're on Earth, so we're considering the Earth's gravitational field. And again, that position we said on Wednesday was based on that object's height from some zero height reference point. So for gravitational potential energy, which today I'm going to label as UG, again, we can also label that as PEG. UG is equal to mass of that object times our acceleration due to gravity, which is 9.8 meters per second squared, and then the height that that object is above some zero height reference point. Okay, this equation we actually utilized in our lab on Wednesday as well. Okay, because we said that the gravitational potential at the top of the ramp was equal to the kinetic at the bottom. All right, now moving into our kinetic energy. And many of us got this expression, or we got very, very close to this expression based on that graph that we created from our data in lab. Kinetic energy is equal to 1/2 times the mass of the object times velocity squared. So again, many of us got this velocity squared piece because we saw that we had a parabolic shape when we just graphed kinetic energy versus velocity. Now, the actual slope of our linearized graph, we should have seen that it was 1/2 the mass of the cart that we were working with. Some of our data was a little bit wonky, so we didn't quite get that result. I think one or two groups did. But this is our mathematical expression that we should have gotten close to deriving through our lab the other day. All right, and then finally, our elastic potential energy equation is going to be 1/2 kx squared. Now, these two variables should look quite familiar to us when we consider springs. Okay, this k value, this is our spring constant. So if you remember back to our forces unit when we looked at some Hooke's law stuff, we did a lab where we tried to determine what the unknown spring constant of a spring was. So remember, spring constant is basically how stretchy that spring is. So a higher spring constant would mean that that spring is more rigid. Lower spring constant would mean that it is more stretchy, for lack of a better term. Okay, and then this x value here, this is basically what we say our deformation length. And again, deformation can be a stretch or it can be a compression from that spring's natural length. Okay, so there's the three mathematical expressions that we have for those three energy accounts. Let's get into that COE modeling packet at this point. All right, so real quick, we'll just go through a couple of these scenarios that you were creating LOL diagrams and conservation of energy equations for. So we'll go through numbers 1 and 2. So number 1, we have a crate propelled up the hill by a tightly coiled spring. So again, our first step is we're going to identify the objects in our system. So we're going to say crate, spring, and I'm going to say earth. You could also include the hill, that's up to you, but these are the three objects that I'm going to identify in our system. So our initial snapshot, this crate is pushed up against the spring, it's not moving, and it's at our zero reference point in terms of height. So that would mean then that we would only have elastic potential energy here. Okay, that's our initial snapshot. Now our final snapshot, we need to be careful here because we are now at some height, but we are also moving. So this elastic potential energy that we had initial, it actually got transferred to our kinetic account and our gravitational potential account. And again, I'm showing that we have 1, 2, 3, 4 bars of energy here. I need to be showing that these two together need to equal 4. That's conservation of energy. So I have 1, 2, 3, 4. So we're good there. Okay, now the physics is done. We've identified how the energy is being stored in these different accounts initially and finally. So we let this now create our conservation of energy equation. So I am going to have elastic potential initial equal kinetic final plus UG final. So that's number one. Number two, we'll go through this one as well. We have a bungee jumper falling off a platform, stretch limit of the cord. So again, the objects in my system will have jumper, we have our bungee cord, and then we also have the earth, or we always include the earth. So initially, our bungee cord is not stretched or compressed, so we have no elastic potential energy. We're told that the guy is not moving, but we are at some height above our zero height reference point. So that would mean that the only account that is being filled is gravitational potential energy. Now, our final snapshot, our bungee jumper has done his jump. So we know we're looking right at that moment at the bottom of the jump when that cord is completely stretched. Our bungee jumper is not moving, so we don't have any kinetic energy, but you will notice that we are still at some height above our zero reference point. So we still have some gravitational potential, but then the rest of that energy is now being stored in our elastic potential account. Okay, so once again, I showed initially we have 1, 2, 3, 4 bars of gravitational potential, and final I'm showing 1 bar of gravitational, and then 1, 2, 3 of elastic potential. Okay, physics is done, so now we write our conservation of energy equation from our LOL diagram. So I'm going to have gravitational potential initial is going to equal gravitational potential final plus elastic potential final. So those are the first two scenarios. Take a look at the last two with those around you, compare, come to a consensus on what those need to look like. We are now going to shift into part 2 of this, which is those problems numbers 5 through 12. Okay, so here's where we're going to get started with the actual problem solving process. Now, this, after we do the LOL diagram and we do the conservation of energy equation, we create that equation from our LOL diagram, the physics is really done. This becomes just an algebra plug and chug exercise. But I do want to go through one of these so we can see this process. So using your conservation of energy equation from question 1, if the spring was compressed 2 meters and has a spring constant of 100 newtons per meter, the crate has a mass of 5 kilograms, final velocity of the crate is 5 meters per second. How tall is the hill? Okay, so we're really focused on that final snapshot, determining how high that box is, how tall that hill is. So first thing I'm going to do is I'm going to identify the known information that we have, and we have a lot in this problem. So we'll start with spring being compressed 2 meters, so that's going to mean that my deformation length is 2 meters, and again, that's a compression. Okay, the direction doesn't matter, there's no positive or negative there because the x is being squared anyway. Spring constant of 100 newton meters. We know that our crate has a mass of 5 kilograms, and then our final velocity of the crate is 5 meters per second. Okay, so what we can do here is we can start out with that conservation of energy equation that we created. Okay, so that's where we said that the elastic potential initial was equal to the gravitational potential final plus the kinetic final. Now what I can do from here is I can plug in my individual expressions for those energy accounts. So initially I would have 1/2 kx squared, and then that's going to equal mgh final plus 1/2 mv squared final. And now hopefully you can see that this is really just a plug and chug activity. Okay, we're taking the known values that we have and using those to then solve for our height final. Okay, so there's a little bit of algebra involved here. I'm going to plug in all of our values just so you can see what this looks like. So there's our spring constant, there's our 2 meters squared. Our mass here for gravitational potential was 5 kilograms times 9.8 meters per second squared. There's our height final, that's what we're trying to find. 1/2, again my mass was 5 kilograms. And then my V final was 5 meters per second. And then that is squared. Okay? Now if we do our algebra correctly here, and again we're solving for our H final, our height final, we should get a value for that to be approximately 2.8 meters. Okay, so again, just to debrief here, once we create that LOL diagram, the physics is done. From there, you can create your conservation of energy equation. The last piece of the puzzle is you just identifying what your known values are for these different quantities that we have. And then it's simply just plug and chug and do some algebra. Okay, so what I'd like for the rest of class today, work through as many of these problems as you can. These first two, again, are based on the LOL diagram work that you did in numbers 1 through 4. The remaining problems, the answers are actually posted in italics at the end of those. So see how far you can get today. We will circle back to this on Monday. Take care, physics students.